I consider study goal 36 to be one of the big critical central lectures for apes, but I should also add that I have discussed this exact content with a bunch of my fishing buddies, members of my family, random members of the public. This comes up all the time. You guys know that I'm a fisherman, and you're not supposed to eat a lot of swordfish or a lot of tuna because it's kind of bad for you. This lecture will explain why that is. But there's a bunch of weird reasons why this keeps coming up all over the place, like why there's a part of Seal Beach where you can't eat the croaker, but you can eat the lobster. Like, this lecture is definitely one of the interesting ones. I also think it clicks really well. Like, once you get it, you get it. And I hope you'll forgive me. This is one of those longer ones, also, but I think this is a valuable lecture. Study goal number 36. Um, I want to start with this thing that it says on the shared screen, that your body is basically hollow. You're like a tube with sphincters at the end, and that tube has arms and legs and stuff. But theoretically, if you had like floss like tied to a marble, you could swallow that marble. It would work its way through the system, go clink into the toilet, and then you could like floss your whole body. Theoretically, I don't think this is going to be a good idea. I'm sure it wouldn't be pleasant. But my point is that your body is not very intelligent. It's not as elegant as we might imagine it to be. It's not as careful as we might imagine it to be. It's basically like a bunch of stuff that you've consumed wrapped in skin with muscles and juices and hormones and secretions. And we're hoping that we can manipulate that food supply so that useful stuff gets into our cells and lets us run around and make fun of your sister or whatever, and the useless stuff can fall out as we're walking or however that works. And it's kind of amazing, that the fact that you never have to think about it, you sort of assume that it must be really elegant and somehow intelligent. I don't know about you. I always feel that way. It's kind of like my car, right? Like, I don't really know how that works, but I'm sure it's fancy because it starts every time. That's like how your body works, right? Like, I never really had to think about it, but my heart's never had a break. Like, it just keeps on ticking. The heart's doing the heart thing. And I want to talk about the digestion thing. You might remember this was a warm up recently. Some of the stuff that you eat will pass through you because your body doesn't need it. If you accidentally swallow a Lego piece or something, it's just gonna like bumble through your body, and your body's just like, nope, 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 like not interacting with that, and it'll just fall out the other end. And there's a lot of stuff that we get rid of because we're done with it, like dead cells, things that we are unable to digest, like hair. There's like cellular material, like one of your muscle cells needs to be replaced, and some of that old stuff we get rid of. Um, a lot of the stuff that goes into us, we exhale as gases because, gases are bonded into organic molecules by producers, and then we release that stored chemical energy and give off those gases again. So, a lot of what you eat, you exhale. And then there's all the stuff that I think you've all considered, the things that you absorb, um, enter your bloodstream, and kind of soak into your cells. And basically, because your body can do that, you function pretty efficiently. And so um, evolution has favored that over many generations. We don't have to think about it, we can't control it. Our body just sort of pulls out the good stuff, and then that just sort of diffuses into our blood so it can soak into our cells, so that our trillions of cells can get the nutrients they need to, make raw Argentinian sex appeal or whatever it is that you do. It's kind of fascinating how stupid our cells are. And, like that's a casual way to say this. The science-y way to say this is it's kind of surprising how simple our cellular selection process is. And it does make sense. We evolved in an environment where our food was very, very simple. And so our cells don't have to be very picky. I mean, they didn't have to be very picky, because in the environment where we evolved, most of the stuff that entered your bloodstream was of a very small number of possible categories. And basically, if it had carbon bonds, it was either going to be fat or sugar or some kind of carbohydrate. And so, your cells would be like yum, and they would just absorb all those carbon bonds and break them all up and make use of that, and we would exhale the CO2. And it was a very efficient way to run as a human being. Our cells are still the same. We are physically the same as we were as cavemen. You have not evolved appreciably since you were a caveman, but your diet sure has. Humans have taken all the ingredients of the earth and shuffled the cards, and now we're dealing out these crazy combos. So I want to talk about what happens when your cells think it's useful, but it turns out not to be useful. And in a lot of ways, we know that our bodies carry huge loads of useless stuff. Like somebody made an additive to make the plastic extra fluffy. And if that additive gets into your bloodstream, your cells are like, ooh, carbon. And so your cells will just soak it up because they have very simple tools. Diet used to be simple. And that stuff just sort of lives inside your cells, and it doesn't really matter. Like, it's not good, it's not bad, it's just there because your cells were like, oh, this is great, I'll use it someday. But your cells can't digest those compounds of carbon, so they just kind of live in your cells. It's interesting, though, that your cells are not really good at avoiding toxins. Like, they've never had to evolve that ability, because in the environment where we evolved, toxins were very, very rare. Like, nobody died of lead poisoning. And so your cells don't really look out for lead. It's like teachers who don't understand technology don't even know how to look to see if you're cheating. Like, your cells, they don't even know that lead's a bad thing, so your cells don't have a method to select things out. What we're worried about, or rather what we're talking about here, is that some chemical ingredients will enter our food supply, go through the straw, right? Dissolve into our blood. And when they're soaking around all of your cells are like, oh, sweet, this has carbon. But your cells don't realize that they may have just absorbed mercury or something attached to carbon into themselves, into the cells. Now it's in your body. Now it's part of your cellular material. And that's bad for you if you have enough of it. It can be dangerous. And your stupid cells just don't know better. They're like, I don't know, man, it had carbon. I find this really interesting. And by the way, I got to apologize. I've been milling oak trees all day, and I cut my eye. It was like super windy, and like a little piece of oak sawdust went into my eye. So I might look funny. I apologize. It's really, really dreadfully uncomfortable. So I want to show you this little movie that a friend of mine made for us. There's a vocabulary term. So I'll explain the concept. I'll show you the movie, then we'll talk about the concept again. The vocabulary term is bioaccumulation. Remember, we're in study goal 36. And bioaccumulation is when things accumulate in life, bioaccumulation, when things are absorbed because they look useful, but they never actually get digested and they never get disposed of because they're not something that we can chemically digest inside of our cells, and they're not something that our cells have practice getting rid of. So we don't use it, we don't digest it, we just soak it into our cells, and then we just, I don't know, maybe I'll figure out what to do with it later. They just pile up, they accumulate. Watch this. This is a fish. And you can see the fish is eating little squares. As the fish goes, the squares disappear. Right? Like the squares are being incorporated into the fish's body because the fish is growing and those squares are being digested. You could say that's sugar, fat, protein, whatever. But look at the dots. Those little dots, they're just piling up. In the course of this fish's life, it will consume a bunch of food that, helps the fish grow or gets crapped out of the fish. But in the course of this fish's life, it's like building a collection of those little dots. They look useful, but they're not. You could say that it has accumulated in the course of its life little dots. My problem is I have so many metaphors and examples that I always mix my metaphors. Let's focus on fish for a minute. Maybe you've heard that some fish have a lot of mercury in them, right? Fun fact, mercury actually is not a big deal if it's pure. Now, you'll never find pure mercury. So if you ever have access to mercury, you should consider that poison. But if I had like a jar full of pure 100% elemental mercury, it's impossible to find really on the surface of the earth, but if it was pure mercury and you swallowed that, pretty fair to say that almost all of that would just fall out in the toilet tomorrow. Our bodies don't absorb mercury, is the funny thing. It's like when a cat is watching a toy but decides not to play with it, right? So you roll a golf ball in front of the cat and the cat's like, uh-huh. And they're like not going for it. That's mercury. Like mercury passes through your body and your body's like, but most of the mercury that you find is not elemental. I already told you that. Don't go playing with mercury, because if you can find it, chances are it's been around on our planet enough that carbon got stuck to it. When carbon gets stuck to it, our cells get excited. Our cells are like, oh, great, this is useful now. Stupid cells don't know better. So this right here, that's a methyl group. So you can have anything like mercury with methyl stuck to it. The methyl is the CH3. And you should write this down for sure. It's a process. It's called methylation. When you attach a methyl group to something else. And we could say that now this mercury has been methylated. The name of this compound is methyl mercury. And most of the mercury on our planet has interacted with microbes that stick carbon groups onto it. Now, once mercury has been methylated, your cells didn't know what mercury was 5 minutes ago. They still don't. But this little thing makes your cells get like really excited. Like, oh yeah, yeah. And then your cells will like soak it up. Funny thing is, when that methyl mercury reaches your cells, it's not sugar. So they can't like do cellular respiration. And it's not fat, so they can't do whatever cells do with fat. And it's not like a carbohydrate, so they can't, whatever cells chemistry, you've got all this chemistry that's good for the stuff that you evolved with, right? So like the basics of your nutrition from your evolutionary past, your cells can do that chemistry. I don't even know what it's called, take a nutrition class, but your cells can handle sugar and carbohydrates and fats and yada yada, but they can't handle methyl mercury. They're just stupid. They're like, I don't know, carbon, great, we can do this. And then once it gets into your cells are like, I don't know what to do with this, but I'll keep it because it's carbon. It's funny, people like talk about detox, like your cells can't detox because they're just stupid. They're very simple, so they just go, I don't know, carbon, we keep it. And like, you can't like drink lemon juice to make them get rid of carbon. There's like one example of methyl mercury pollution that's really world famous. You got to know this one. It's like the worst mercury pollution that humans have ever faced. There was like an industrial mercury facility, and like I can't remember if they were like taking out the trash, or like if a ship sank, or like if a shipping dock broke, maybe. I don't know, man. Anyway, a whole bunch of mercury, like barrels and barrels and barrels, like a warehouse full of mercury, fell into this bay in Japan. It's called Minamata Bay. It's on the screen and you should write it down because it's famous. It's one of those classic examples. And like it took a while, because once that mercury started to like fall out of the rusty barrels, like stuff at the bottom of the bay, decomposers, microbes, whatever, eventually that mercury started to get carbon attached. And when there's carbon attached, the algae are like, oh, sweet carbon. And they think it's useful, but they can't use it. And then like the little shrimp eat the algae, and like the cells of the shrimp will keep the useful parts of the algae, right? So like when shrimp is eating algae, they like, oh, sugar, and they like digest the sugars from the algae, and like, oh, fat, and they like digest the sugars from the algae, or the fat from the algae. But all this methyl mercury was in the algae, and all the shrimp were like, oh, great, yeah, carbon compounds, this is going to be good. And then the shrimp just got packed with mercury, but they didn't have a way to digest this. And then all the fish that eat the shrimp, and then all the big fish that eat the little shrimp, eventually the levels of mercury in those larger animals were massive, because think about it, a big animal is eating like so many little things that ate so many little things that ate so many little things. That covers a lot of landscape, right? Over a longer period of time, right? Because larger things tend to live longer. And then, you know, in Japan, humans eat a lot of seafood. And this was like a seafood community where people just eat seafood like 24/7. And there were like a whole generation of children born with like horrific birth deformities and like developmental disorders, and like really, really, really sad. Like, if you want to bum yourself out, you should Google Minamata Bay children or Minamata disease. Minamata Bay disease. It was like a set of symptoms that children were often born with. Really horrific, major example. But here's what happened. Bioaccumulation is when cells keep things which appear useful but aren't. That's a good definition. You should write that one down. God, my eye's killing me. Bioaccumulation is when cells keep something that appears useful, but it turns out not to be useful. That's accumulation. But what happens in a food web when all the organisms have the stuff that they accumulate, right? You remember how one fish might end up with a bunch of little dots, right? Here's a reminder, that little fish is about to eat a square, digest and use the square, and then gain another little dot. Now you've noticed this animation includes another organism. We're throwing in a predator of the little fish. And you know, the little fish disappear, right? The little fish, when they're eaten by a big fish, they kind of leave the scene, right? Because they got digested by the big fish. They became big fish, or they got crapped out by the big fish. So you've got your bioaccumulation happening in the little fish. And when the big fish eats the big fish is also accumulating the little dots. But imagine how many little dots end up in a big fish. It's a lot of dots. And then imagine when a human eats that. The concept that I wanted to show you here is called biomagnification. The idea that the useless stuff accumulated in a small organism is less than the useless stuff accumulated by one step up, right? Because like if this was crickets, you've got a whole bunch of crickets, all their useless stuff goes into one mouse. Now the mouse has all the useless stuff of however many crickets it could eat in its life. And now if you imagine like a rattlesnake that eats a whole bunch of mice, there's this thing called biomagnification, which you could visualize as a funnel. You all know what a funnel is, right? Like the pictures on this are totally horrible. Whoever made these slides or these images blew it, but I really needed them anyway. here's the thing I want to point out about this. You know, like one mountain lion, that's not a mountain lion, but one mountain lion might eat a whole bunch of coyotes in its lifetime. And each of those coyote might eat a whole bunch of deer in its lifetime, probably not an adult male, but anyway. And then each of those deer is going to live a long life grazing on the landscape. Now, if that landscape had been watered with methyl mercury in solution, then the plants would all accumulate methyl mercury, and then that would end up in the deer, and then tomorrow's methyl mercury would end up in the deer, and then the next day's methyl mercury would end up in the deer, and you'd have a whole bunch of deer going into a handful of coyotes going into one top carnivore. And so all the methyl mercury for all those days from that entire landscape is finding itself into a lion for the entire duration of that lion's life. So the amount of accumulated biotoxins is greatest at the top of the food chain. That's biomagnification. The amount of accumulated biotoxins is greatest at the top of the food chain. That's why you can't eat too much tuna or too much swordfish, because those are the big predators of the ocean. You can eat a whole lot of shrimp and you don't really have to worry about mercury, because at their level, you could eat shrimp for a whole lifetime and really not reach a significant number. But think of all the shrimp that went into all the herring, that went into all the mackerel, that went into all the tuna that I have eaten. Like, I couldn't eat that many shrimp in my entire lifetime, right? Because all their energy gets spent, right? That 10% rule, right? So like, 10% and then 10% of that and then 10% of that, right? So like, I'd have to eat 1,000 shrimp for every calorie equivalent of tuna that I've eaten. Whatever, you know what I mean? 1,000 to 1, because it's like 3 steps. And here's the thing about the ocean. Fun fact, in the ocean, it's not like 4 or 5 layers. Ocean food webs usually have like 2 or 3 different layers of plankton, and then 2 or 3 layers of small fish, and then 2 or 3 layers of medium fish, and then usually 1 or 2 of large fish. And then even most of those are also cannibalistic. So when you eat a trophy tuna, you're eating like a pyramid with like 9 to 10 to 11 steps. So all the mercury that happens to be dusted into the ocean, fossil fuels are burning a lot of fossils, so we're adding more mercury to the atmosphere. That's why this is a modern problem. You think of all that mercury that's falling on the surface of the ocean. You could drink that water, you'd be fine. It's not a lot of mercury. You could eat that algae, you'd be fine. There's not a lot of mercury in the algae either. But if you take all of that oceanic square mileage, right? When you feed all of that algae to the plankton, they're going to use up all the calories, right? So there's not a lot of calorie value left in all those plankton, but they still have every last drop of that mercury. Now, all of that mercury gets fed into larger plankton. And again, 90% of the caloric content is burned away in the life of those plankton, but all of that lead is being stored there. And so on and so on and so on until it reaches the tuna. This is biomagnification. I always feel like I understand it better than I say it. So I hope you can ask me questions about this, because I can tell you it's an important topic. It'll show up for the rest of your life when you're a grown up, like when you're pregnant or when your wife is pregnant and you're like trying to think about whether or not you should really worry about this mercury thing. Like, here's the reason. Like, you should really learn this one. It's important. All right. I'm going to stop this one.